Hi guys, so here we are at the beginning of our last unit, Unit 7. Unit 7 is Earth Systems and Agriculture. So the first half of that is the Earth Systems part. We get to talk about geology, which is my favorite. And then we're going to talk about an application of that when we talk about mining in Chapter 23. And then we're going to talk about soil basics in Chapter 9, and then how all of that plays into agriculture. We've talked about the size of the human population. So now we're going to look at the challenges of feeding that population. But that's down the line. So let's get started with Earth science stuff. So this chapter is technically titled Earth's Physical Systems, Matter, Energy, and Geology. The text goes through thermodynamics, and basic chemistry that you guys have gotten already. That's outside the scope of our class. So I edited the presentation, 31 slides. Let's see how fast I can get this done. So this slide was full of objectives, but this is all we're going to talk about. Most of it's plate tectonics, not so much the rock cycle, although we do have to talk about parts of it. And then we're going to look at how geologic hazards happen, and then how we can make them less of a thing. So this is the case study. This is the article you guys are going to read on the Tohoku earthquake. So in 2011, so 10 years ago, a huge earthquake, a 9 on the Richter scale, hit the coast of Japan and generated a tsunami. It topped over an 18-foot seawall, and I actually have a video from this area that we'll watch. And it also, when it topped that seawall, it shut down the nuclear power plant, Fukushima Daiichi. We talked about that when we were in Chapter 20. So it didn't damage the power plant itself. What it did was it flooded the backup generators. So the earthquake caused the power to go out, and then the tsunami took out the backup generators, which caused the meltdown that we looked at in Chapter 20. So you guys are going to read a little more about that. So if we look at the elements in the Earth's crust, okay, within the Earth, the most common are oxygen, hydrogen, silicon, nitrogen, and carbon. Silicon, not silicone. All right. So it's interesting that it's a 2-to-1 ratio in the Earth's crust, and we'll talk about why. Well, I can tell you why right now. The most abundant mineral is SiO2, so it kind of makes sense. So you can look at the common elements in the crust, the ocean, the air, and then in organisms. Oxygen is in the top 2 in all of them. So if we talk about basic chemistry, we look at the term isotope. An isotope is an atom of an element that has a different number of neutrons. So we talk about radioactive isotopes of uranium. And we look at different isotopes of carbon, carbon-12, which is, the most common carbon, and carbon-14, which is also radioactive. So an isotope just has a different number of neutrons. Some of them are radioactive, which means they decay, and then they change their identity. And we've talked about that, okay? They are most damaging when they enter living things, because those neutrons that pop off will wind up doing damage to tissues. So after Fukushima happened, scientists started testing food and water for the presence of radioisotopes. Okay, and we're going to do some math on this. So radioisotopes are going to decay into smaller and smaller and smaller parts until eventually they're going to become stable. The idea of a half-life is the amount of time it takes for half of the atoms of a particular radioisotope to decay to another kind. Cesium was the radioisotope in the Chernobyl power plant and also in Fukushima. So It's got a half-life of about 30 years. So you can see how it, you get spikes when the releases happen, but then it calms down after that. So we can talk about sources of energy from the planet. We talked about geothermal energy before. What causes geothermal energy, that heat from inside the earth that we can harness to create steam to turn turbines to generate electricity, comes from the fact that radioisotopes naturally occur within the inner layers of the earth. Okay, so they decay, they release heat, and then that melts the rock that's below the surface to generate magma. Okay, and magma comes up and comes from volcanoes. It moves plate tectonics, moves a plate through the process of plate tectonics, and it heats groundwater, like I had mentioned when we talked about geothermal energy. That water that's heated by geothermal energy can come out of the ocean crust in areas called hydrothermal vents, right? And we've seen them, or we'll look at them in our chapter 2 discussion, the key points. There's a huge body of life that exists where this warm, mineral-rich water comes out of the Earth's crust. And those organisms use hydrogen sulfide to produce sugar in a process called chemosynthesis, which is photosynthesis essentially without light and using different compounds. So there's your glucose that comes out of this process, and you get sulfuric acid is one of the byproducts. It's actually pretty cool. We didn't think that life existed way down there at the bottom of the ocean because there's no light that gets down there. So what the heck could be powering it? And then in the 60s or the 70s, I'll find out, they discovered the life on the hydrothermal vents, and it was pretty cool. Okay, so here's the meat and potatoes of what we're going to get at. And this is something that you guys don't cover really ever in high school. You get it in middle school and you understand pieces, but we're going to look at how it relates to our course. So if you take a look at it, geology is the Earth's physical features, the processes, and the history of the planet itself. It's the rocks and how they formed. The processes that we talk about in geology shape the landscape. Okay, they are the base component for all of the environmental systems and ecosystems that we have on the planet, and they are the reason why metals and fossil fuels exist where they do. So when we get to the next chapter, which is on mining, geology is the reason why mining can take place. So the Earth consists of layers. You guys need to know what those layers are. All right. So in terms of chemical composition, we look at the core, which is in the middle, right? It's there's two parts to it, the inner core and the outer core. So the core is this red and brown part. The inner core is solid, it's iron and nickel. And the outer core is liquid, okay? So the inner core, why is the inner core solid and the outer core liquid? The inner core is solid and the outer core is liquid because the inner core is under more pressure than the outer core. So that increased pressure gets the atoms close enough to become a solid, all right? At the outer core, there's less pressure, so temperatures are high enough and the pressure is low enough to make it liquid. And the inner core spins within the outer core, which is what generates the magnetic field that the Earth has, okay? Outside the core is the mantle, and the mantle has two parts. Okay, the lower mantle, which is more solid, and then the upper mantle. Okay, this is solid-ish. Okay, actually, this is all the upper mantle. Okay, there's a zone of silly putty-like rock. Okay, it's solid, but it's not super solid. It'll flow like silly putty under force when force is applied. It's called the asthenosphere. It's one of my most favorite geology words, or the asthenosphere. It's just cool to say. So the mantle is the middle layer. And like this says, the asthenosphere is the smushy, soft, flowing rock, okay? And the lithosphere is composed of the uppermost part of the mantle and the crust, okay? So we talk about it in terms of physical properties. We've got the lithosphere, the asthenosphere, the mantle, or they call it the mesosphere, the outer core, and the inner core. If we look at it in terms of chemistry, we've got the core, the mantle, and the crust, okay? And it's stratified by density, okay? So the most dense things are on the inside, and as you progress further out, density is going to decrease. At one point, the Earth was homogeneous, so it was like a well-mixed cup of coffee. If you put sugar in it and milk and you stir it up, then the first sip is going to taste the same as the last. But then the Earth started to cool and then stratified according to density. It's pretty neat. So a lot of the features that we have on the face of the Earth exist because of plate tectonics. This is the current world map. The world has not always looked like this. At some point, you guys have heard in your previous studies about the idea of Pangea. Pangea meaning all Earth was surrounded by an ocean known as Panthalassa, meaning all sea, as recently as 250 million years ago. Okay, so how did we get from this Pangea picture to what you see on maps today? It's the idea of plate tectonics, okay? Underneath the surface of the Earth, in the mantle, you have convection taking place as the result of the core heating the magma and melting it to some degree. So that's going to create a convection current. That magma current is going to rise towards the surface because magma, because it's hot, is less dense than the surrounding rock. It's going to rise to the surface. It's going to bump into the lithosphere over top of it. And depending on how the convection currents in the asthenosphere line up, will give you different kinds of plate motion. And you can see here that boundaries can be divergent, transform, or convergent. There are divergent boundaries that run through all of the oceans, and we are definitely going to talk about them. So at a divergent boundary, like you see here in picture A, the plates are going to move apart. So what's happening here, convection currents are coming up on the right-hand side, okay, and moving away, and up on the left-hand side and moving away. So if the convection currents are diverging, it's going to drag the overlying lithosphere with it, okay? So as the magma rises to the surface and cools and moves away, it's going to create a divergent boundary. This is the mid-ocean ridge, right? So it's what they call a rift zone. At a transform boundary, okay, these convection currents are rising, but they are not aligned horizontally. Okay, they're not lined up perfectly with each other. So it doesn't really matter what direction they're moving, they are offset. So it's going to make the motion offset. Okay, so that's why they call this a strike slip fault. I don't like the fact that, so they're going to grind alongside each other. So there's going to be motion along here. One's coming one's moving into the page, or one's moving out of the page. This says it causes earthquakes. You get earthquakes at a divergent plate boundary too. Wherever you have large masses of rock moving, you're going to have earthquakes happening. So this is the San Andreas Fault out in California. That is the classic example of a transform fault. There's actually 3 possible actions that can occur at convergent boundaries. You can have convergent boundaries that are 2 pieces of oceanic crust coming together. You can have a convergent boundary where you have oceanic and continental crust coming together. And then the third kind is having 2 pieces of continental crust come together. All right. So when you have this, it doesn't show you here, which is annoying. But if you have 2 pieces of oceanic crust coming together, whichever one is more dense, so typically it's the one that's older and colder, is going to be pushed underneath back down into the asthenosphere in a process called subduction. You can see this picture here. All right, just pretend that this continental crust plate is an oceanic plate. Okay, so you're going to have this piece of oceanic crust subducting down into the asthenosphere, Okay, it's warmer down here, so this is going to melt and it's going to rise, right? Because magma is less dense. And if this is oceanic crust, it's going to pop through the oceanic crust, creating volcanic islands, okay? Like Japan, like the Philippines, like New Zealand, like the Aleutian Islands in Alaska. Not like Hawaii. And we're going to talk about Hawaii, so don't worry, okay? So you get a volcanic island arc in that case when two pieces of oceanic crust come together. When a piece of oceanic crust comes together with a piece of continental crust, we can talk about this. The oceanic crust is more dense than continental crust. Continental crust doesn't subduct. It's like trying to, you guys know when you get into a pool and there's like a beach ball, you did at one point, because I know you all did. You try to sit on the beach ball to make it stay underwater. Right? You lay on it, you sit on it, you do something. But if you wiggle the wrong way, that beach ball is going to pop right back up. And that's what happens with continental crust. You can put mass, right, on top of the continental crust and it'll go down a little bit like it did during the last ice age. It'll subside. But once that force is removed, it's going to pop back up, right? It's less dense than the asthenosphere, so it's not going to subduct. So when oceanic crust and continental crust come together, the oceanic crust is going to subduct because it's more dense. Just like I mentioned in the ocean to ocean convergent boundary, this subducted plate is going to melt, turn into magma, and rise. In this case, instead of breaking through oceanic crust, it's going to break through continental crust. And you're going to get a coastal volcanic mountain range like the Andes in South America and my favorite, the Cascades in Washington. So Mount St. Helens is the result of an ocean to continent convergent boundary, which is really cool. All right. The third kind of convergent boundary is a continent to continent convergent boundary. Okay. So when that happens, when you have two pieces of continental crust coming together, there's no subduction. Okay. So there's no magma. So these two big, thick piles of continental crust push up on top of one another to create really, really high mountain ranges, okay? They crush, they bend, they buckle, and they go upward to create mountains like the Himalayas, right? So this is India pushing in under Asia to create the Himalayas. And as long as the convection is moving in the asthenosphere, all of these boundaries are going to keep happening, okay? So as long as convection is pushing India into Asia, then the Himalaya mountains are going to keep getting taller and taller and taller. All right. So that's the three kinds of boundaries that you can get when plates come together. So we can talk about what a rock actually is. So in order to do that, we have to talk about what a mineral is. I remember this definition of mineral from my introductory geology course in college. A mineral is a naturally occurring inorganic solid with a definite composition and a definite internal structure. Okay? Naturally occurring solid element or inorganic compound with a crystal structure, a distinct chemical composition, and physical properties. So you can identify minerals based on these factors. And I had to do that many times in my mineralogy course. You put a bunch of minerals together and you get a rock. It's just simple. So minerals are the building blocks of rocks. Over time, rocks and minerals go through this process called the rock cycle, okay? That takes rock and melts it, breaks it down, reassembles it, heats it, cools it, all of these things. So we'll look at that right now. All right, it's a cycle, so you can start in any particular spot. And if you look at this, you can get the way it really should be is you can get any rock from any other kind of rock, which is kind of strange. All right, so this starts us with magma, right? So magma is liquid rock below the surface. Once it gets close to the surface or at the surface, we call it lava. So now you know the difference. When that cools and crystallizes, it becomes an igneous rock. There are two kinds of igneous rocks. Sometimes that igneous rock forms below the surface and the crystals get big. They call that an intrusive igneous rock. That's like granite and that kind of thing. If it comes to the surface and comes out, they call that an extrusive. It's been extruded from inside the earth. It's an extrusive igneous rock. And that's basalt pretty much, okay? So you can melt a metamorphic rock. There should be an arrow going from metamorphic rock. Well, it is here. You can melt metamorphic rock and get magma or lava as well. But igneous rock comes from liquid rock, magma or lava. Okay. If you weather, erode, transport, and deposit, so if rain and snow and wind break any kind of rock down into smaller pieces, right, and it gets transported, picked up by water is one of the main modes of transportation for these little pieces, these sediments. Okay, here they are. And they get laid down somewhere. You get sediments, little bits, sand, dirt, mud, gravel, stone, anything like that. Those are considered sediments, those little pieces. They get exposed to some kind of pressure, not a whole lot of pressure, okay? Or they have some kind of natural cement that forms them, and they lithify meaning turn to rock, and become sedimentary rocks. Let's see what the next slide has. There's intrusive and extrusive igneous rock. Sorry about the delay. That's Yosemite, and then basalt. It's ropey. It's kind of cool. All right. So the sediment layers that we had talked about accumulate and get buried. This is Antelope Canyon. This is wind-blown sandstone out in Arizona. Some of the most beautiful places I've ever been in the whole wide world. So these little layers, these little bits, these sediments accumulate together and form sedimentary rock like sandstone, conglomerate, mudstone, shale, which there's a lot of around here. Okay, if I go back to this, I like the rock cycle. You put a little heat and a little pressure on any of these rocks, not so much that it melts, right? But enough to make the minerals realign. You get something called a metamorphic rock, right? They tend to be harder than most other rocks, okay? If the physical properties get changed by the heat and the pressure, they call it a metamorphic rock. So this is nice. Yes, this is a nice rock. Get it? Nice. If you take granite and expose it to heat and pressure, not enough heat and pressure to melt it, but enough to make the minerals realign, you're going to get nice. And it actually is a pretty nice rock. So, Earth has been around for 4.5 billion years. Okay. They divide it based on time and normally based on extinctions. There's 3 eras and 11 periods, and then each period is subdivided into an epoch. Okay. So you determine the period based on what you see in the strata or the layers of rock, mostly sedimentary rock. So our current period is called the Quaternary, and it began about 2 million years ago. The current epoch is called the Holocene. But there is some conversation that we need to create a new epoch based on things that have been happening over the course of the last 200 years. They want to rename or call the new epoch the Anthropocene. So anthro is human, right? So the human-induced epoch. Based on the fact that the last 200 years, things have changed so tremendously. And there's a really good book that we can talk about that I read in about a day that talks about this. More evidence to support the fact that we should call it the Anthropocene, but they haven't yet. All right, so we talked about moving plates. We talked about the rock cycle. How does that have to do with geological hazards? So this is what they call the ring of fire, right? If I go back to, oops, wrong way. Sorry. if I go back to this picture, okay, these are all the plate boundaries in the world, and this map is focused on the centered on the Atlantic. But if you look around the Pacific Ocean, okay, there's a lot going on over here, right? Japan, the Philippines, oodles and oodles of earthquakes going on, all right? So they call that the Ring of Fire. There it was, okay? 9 out of 10 of the earthquakes and volcanic eruptions that take place on the planet take place around the Pacific, because that's where the big plate boundaries are, some of the most active plate boundaries are. So what an earthquake is a release of energy at a tectonic plate boundary. So when an earthquake happens, okay, something you guys might not recognize or realize is that when you have two really big masses of rock stuck right next to each other, okay, there's friction between them, okay? So those rocks are going to apply force and force and force and force. And rocks will actually bend. Okay, there's so much force applied to them because they're such huge masses of rock that they're going to bend and bend and bend and bend. And then all of a sudden, the rock can't take it anymore. You know, the bonds between the minerals or the atoms in the minerals of the rock just can't take it anymore, and they break. So all of that built up force is released. So when the rock breaks, the earth is going to shake, and that's what causes an earthquake. It's all of that energy stored in the fault, the boundary between those two plates, when it gets released really suddenly. So the rock breaks, the earth shakes, and then the rocks will actually move, okay? Depending on which direction. They're either going to move towards each other a little further, they're going to move apart from each other a little further, or they're going to slide. Sometimes they can occur on the insides of tectonic plates, and we're going to look at that in a minute, because of other processes, you know, failed rift zones and smaller degrees of convection that are happening within the asthenosphere. Engineers frequently, especially in developed countries, they have ways to protect buildings from shaking, okay? And we used to teach a class in here at Del Valle. It was called General Science, and we did a project where kids would design an earthquake-proof structure, and it was actually really cool. So just like a good tree, trees should sway in the wind, just like the flagpole, right, that Walter had talked about. So they're supposed to sway. You want them to bend so they don't break. Developed countries have that. Developing countries don't, okay? So, there was an earthquake in Haiti in 2010 that killed almost 250,000 people, right? There was also an earthquake that same year in Chile. It was a bigger earthquake, and it didn't kill near as many people because the building codes and the regulations in Chile are much more stringent than those in Haiti, and we're going to talk about that when we do our key points for this chapter. So your highest risk is the red, right? We are not really in that much of a risk zone. A little bit of yellow, okay, because of the Ramapo Fault that's in North Jersey. But a couple places that are, okay, this makes sense. The whole West Coast makes sense, right? Because it's California. The San Andreas Fault is out here. You know, this is the subduction zone of the Juan de Fuca plate under the North American plate to make the Cascades. Hawaii is volcanically active, right? We know that. Well, we'll talk about why that is in a second. There's a lot of tectonic activity going on here at Alaska because the North American plate is subducting under the Pacific plate. No, sorry, the Pacific plate is subducting under the North American plate. This is the Yellowstone, right? So there's a hot spot there, which we'll talk about in a second. These two are kind of perplexing, okay? We'll talk in the key points about what's going on here in like Missouri, Arkansas, Kentucky, Illinois, Tennessee, and what's going on over here in South Carolina. But there's a reason for it. So volcanoes come from rifts, so when plates are pulling apart, when plates are coming together, or where there are no plate boundaries. We can get volcanic activity where there are no plate boundaries. So it's where anything comes out through the Earth's surface. In many cases, it's where plates are converging, right? Like in the Cascades and in Japan. Japan is the most volcanically active nation. 100 active volcanoes, right? Doesn't mean they've erupted recently, but there are 100 active volcanoes. Lava can also be emitted at a hot spot, which is an area where it's exactly what it sounds like. It's a hot spot in the mantle, and then that plume of magma rises up and breaks through the overlying crust, either oceanic crust or continental crust. So this is Hawaii, right? Hawaii is a hotspot volcano. Hawaii is in the middle of the Pacific Ocean. There are no plate boundaries surrounding Hawaii, right? It's not on a boundary. It's smack in the middle. So don't tell me that Hawaii is, a convergent, what forms as a result of a convergent plate boundary. No, right? So in a hotspot, the hotspot stays put. And then the plate moves over the hot spot, okay? So this is the location of the hot spot. You can trace the movement of the Pacific plate over the course of the last 60 million years. So it's actually kind of cool. These are the Hawaiian Islands, right? And this is Midway Island, where we got the albatross boluses from, right? And then this is what they call the Emperor Seamount Chain. So at some point, this part of the plate was here over the hot spot. So then the plate was moving north until convection in the asthenosphere changed, and then the plate started moving on more of a northwest trend. So at some point, this part was over here, and it's moving in that direction. Now, this is the big island of Hawaii right now. These are the present-day Hawaiian Islands. There's a new island that's forming because the plate is continuing to move. It's called Loihi. So if you save your money in about 2 to 3 million years, you can be the first to get oceanfront property on Loihi. I don't think it's going to be, super fabulous. It's still going to be volcanic and erupting, but you never know. Whatever floats your boat. As different kinds of volcanoes erupt, different plate boundaries form different kinds of volcanoes, and the different kinds of volcanoes have different hazards. So the Hawaiian Island volcanoes are what they call shield volcanoes. So they just blurp out lots and lots of lava. Kilauea on the big island of Hawaii has been erupting lava daily since about October 1983, right? That's a long time, and it just blurps and blurps and blurps. Sometimes it's more active than others, but it's relatively predictable. Mount St. Helens was a little more violent. It didn't release a whole lot of lava, but it released a lot of ash and cinder, and put a lot of sulfur dioxide into the atmosphere back in 1980. And you guys all heard about the city of Pompeii, right? And Mount Vesuvius in 79 AD. It was a huge, massive eruption that put what they call a pyroclastic flow of ash and gas and rock that moves very, very quickly, 725 kilometers an hour. And you can't outrun it, and you can't outdrive it, and you can't outfly it. So you're basically dead. And it destroyed the city of Pompeii and also the city of Herculaneum as a result. So different kinds of volcanoes have different hazards. And we talked about this, right? That the eruption can affect people around the world. Like when Tambora erupted in 1815, it put enough ash and sulfur dioxide into the atmosphere to create a global cooling effect, right? It reflected the radiation anywhere between half and almost 3/4 of a degree Celsius in the years afterward. So it can have global impacts. There is a process called mass wasting, where you have, chunks of land that will just fall away from where they're supposed to be. A landslide is an example of that, when you have a huge amount of rock or soil that collapses and then just flows downhill. There was one out in California not too long ago that destroyed part of the Pacific Coast Highway. So they're real things. When you have an earthquake that causes a large change in seafloor topography, all right, whether it's an earthquake, a volcanic eruption, or a big coastal landslide, it can generate a tsunami. A tsunami is not a tidal wave. It's called a seismic sea wave. And we can talk about how they form. So the tsunami that hit Japan, 10 years ago was triggered by an earthquake, that big earthquake, that magnitude 9. A tsunami the day after Christmas in 2004 hit Indonesia. Okay, there was a slip, a subduction zone slip in the seafloor, and it generated a huge tsunami in the Indian Ocean. There was no Indian Ocean warning system for tsunamis at that point. There's been a Pacific Ocean tsunami warning system for a long time, but there wasn't one in the Indian Ocean. So by the time the wave hit the Pacific Ocean sensing buoys, there was no way to warn people. So almost a 250,000 people died as the result of this tsunami. I clearly remember it. Nations collaboratively have gotten together to do what they can to improve warning technologies, to let people know that things are coming. Something else that could be helpful, moving away from the coastline could be helpful to keep developed areas protected in a tsunami. And then mangrove restoration would be great, not just for in case of tsunamis, but for the imminent sea level rise. So what can we do? All right, they're natural hazards, but things that we do can make their effects worse, right? So if we live in an area that's prone to hazard, so if we live in a floodplain, if we live in a tsunami zone, if we live in an area where a volcanic eruption is possible, we are increasing our risk, okay? But again, that goes back to the cost-benefit analysis. This is a cost, but is the benefit worth the risk? If we alter natural rivers, we can wind up with greater flooding. If we clear cut forests on slopes, there's nothing to hold that soil in place. So that's how you're going to get landslides and mass wasting. And climate change, human-induced climate change. We're going to see sea levels rising, right? So if sea levels rise and you get a tsunami, it's going to have a much bigger impact inland than it would before the idea of before sea level rose. So we are adapting, and we're also mitigating when it comes to these natural hazard risks. So that's a little bit about plate tectonics and Earth systems, and we'll talk more about some details in our key points.